Okay. All right, so I just added on the far right, we'll just make use of that little space. You'll be so kind. All right, so today we're gonna continue with the nerve impulse discussion. You're gonna be glad you're here because we're gonna keep up with some of that harder stuff. And then we're gonna finish the nervous tissue chapter. If we have time, I want to start the central nervous system. Okay? Don't forget, we don't have lab this week. I don't think you forgot about that though, right? Probably not. So no lab. When we return next week, our next lecture exam is a week from Thursday. So it comes up quickly, but the reason I do that is because I want to give you a week, more than a week, in between that last lecture exam and the final. So I know it comes up quickly, but that exam 4 will only be on whatever nervous tissue we've covered until then. All this means is that you want to keep up on the material. I know you're busy, it's a busy time of year, but whatever you can do to keep up on the material. I'll see you again a week from today, but then that following Thursday, we'll have an exam. When we return to lab next week, we have a spinal cord lab next week, but there's no quiz in lab next week. There's nothing due in lab next week. So just show up. Last week, I gave out the final exam review. I brought them again in case anybody didn't get one. Or if you want a second copy, I don't know, so I'll keep them here, you're more than welcome. Any other questions, comments? After Thanksgiving, we only had 3 weeks. It's a little tough this time of year, you know, because it's. All righty. Unfortunately, I have no other way to do this except to. Yes.
So was it next Thursday for test or was it tomorrow?
A week from Thursday. A week from Thanksgiving. A week from Thanksgiving.
Oh,
There's a sign in my office with a picture of that ugly cat that has its own profile on social media. It's on the syllabus. But it is my job to remind you. That's what I get. All right. And I want to add. I mean, look at me go. This is pretty impressive. Why does it have those lines on it? Look at that. Hey.
So
Go
right
back.
now, this projector is connected to the computer, so connected to your iPad.
Correct. Well, I'm connected to a Zoom meeting. I'm zooming into my own call. Why does it have that? What I'm trying to do is create just a new blank. Blank. I don't want anything else. I don't want that. I want blank. We have a no cover. There was one that said no cover. The other thing. Yeah, that first. Hey, thank you. Okay, so we began our discussion last week talking about nerve impulses. And you were all so excited, weren't you? Heck yeah, man. So we talked about there's 2 types of nerve impulses. So let's just review. We talked about that. We have the nerve impulse that you commonly think of, the full-blown nerve impulse that travels the whole length of the axon. That's called an action potential. When you think of nerve impulse, you're thinking about the action potential, right? But we also introduced that there's such a thing as a graded or local potential, and that is like a mini impulse, right? Does this sound familiar? Okay, so I want to point out to you again some of the major differences between these two. Thank you. The action potential, the full-blown nerve impulse. The full-blown nerve impulse, in order for it to fire, there has to be a threshold that's reached. Not every little stimulus will generate an action potential. What we're going to find out today is we have to reach a certain threshold. And only if we reach that threshold does this full action potential fire. On the other hand, a graded or mini impulse can be generated from pretty much any stimulus. So cells are almost constantly sending mini impulses. The graded potential, the effects are more local. That's why it's called a mini impulse, right? That mini impulse only travels short distances, whereas an action potential has widespread effects, right? If we actually reach threshold and we fire an action potential, it's going to travel the whole length of the axon, no matter how long the axon is. And then the last thing I want to point out for now is that the action potential is really only occurring in nerve cells. Look at this fanciness. Ooh. Ooh. So nerve cells and muscle cells, but nerve cells can create this full-blown nerve impulse, an action potential, versus a graded potential, a mini impulse, can be generated in a lot of other cells too. I love these compare and contrast, how my brain works. Hopefully your brain works that way. If not, you might be screwed. I don't know. That's not true. Okay, so we did talk about how a graded potential is generated. Do you remember this discussion? We're going to do it again. Ooh. It's just weird to be looking down. That's why I don't like being up on the screen. But that's okay. Yeah, I'm a pretty in shape person, Nancy. For a 42-year-old female, I think I'm doing all right. I suppose there's pros and cons to each of them. So let's talk about a nerve cell, right? And we always start from rest. At resting membrane potential, tell me, what is the inside charge of the nerve cell? The inside of the nerve cell is negative 70 millivolts compared to the outside, right? And that is because of the flow of potassium and sodium. Because error message, just ignore it. So we get that negative charge because of the flow of potassium and sodium. So I told you 3 magic words. How do we go from resting to generating a current? 3 words. Open sodium channels. Bless you. Whoever that was. The 3 magic words. Open sodium channels. In my other life, I'm a Broadway performer. So how we get to that first step called depolarization, that's how we described it. The first step towards making a graded potential is something called depolarization. And in depolarization, we open a bunch of sodium channels, right? These are voltage gated channels. We know we have more sodium on the outside of the cell. If we all of a sudden open more sodium channels, sodium comes rushing in from high to low. When sodium comes rushing in, what happens to that inside charge? It turns positive. Let's just give it a number. So sodium's going to come in. The inside becomes positive. Let's say it gets to positive 10 millivolts. We started at negative 70 and we go to positive, it's kind of hard to read the green, huh? We go to positive 10. How many millivolts change is that? 80. So in a split second, just by opening sodium channels, a flood of positive sodium ions rush in, and the inside goes all the way from negative 70 to positive. That is the spark. The quick spark of electricity. We have depolarized the membrane. We created a spark. The next thing that happens is that depolarization wave spreads. How do we do more depolarization? 3 magic words. Open more sodium channels. So let's say that, what can I use that you'll see? So let's say that we started to depolarize the membrane here. So now we're going to spread the depolarization wave. In a graded potential, we spread that depolarization wave in both directions. So now we're going to open sodium channels here, and we're going to open sodium channels over here. And then after this area opens sodium channels, we're going to open sodium channels here. Then we're going to open them here. Then we're going to open them here. I gave you the analogy of the wave. I think we get this, right? So in a sporting event, in a graded potential, one person stands up or depolarizes. It would trigger this person and this person to stand up because it travels in both directions, which would then trigger the next people to stand up. So it's like spark, 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 spark. And if each little part sparks with electricity, you've created a current that's traveling down the nerve or the axon. Now, after an area depolarizes, and after the areas beside it depolarize, the initial area repolarizes. Repolarizes means to go back to its original resting charge. So we're going to turn the inside back to negative 70. How do we do that? So to depolarize, we opened sodium channels. And then that triggered the adjacent areas to depolarize by opening sodium channels. But it's just like the wave. Imagine when you're sitting in your seat, that's it resting. I depolarize, which causes this person and this person to depolarize. But once they depolarize, what do? I sit back down. There we go. Plenty of pictures here for you, right? So we depolarize the membrane. When there's a stimulus, an area opens the sodium channels and it turns the inside positive. And then what this is showing you, in a graded potential, that depolarization wave spreads in both ways. And then after that initial area depolarizes, it will go back to regular, negative 70. Here at the bottom, it's trying to show you that in a graded potential, the initial intensity is high, but the further that current travels, the current gets weaker and weaker. That's true of only a graded potential. Look, the intensity differs which means that the intensity of the gradient potential starts off high, but as it gets further and further away from the initial start, it gets lower and lower. That's why it's called a graded potential. Its intensity is graded. Higher at first, and then it kind of peters out. It's like a wave where eventually it just stops. And of course, this is different from an action potential, because an action potential is going to maintain the same intensity no matter what. So that the ability of the current to change intensity is only true of the graded potential. Good. So here we go. We started off at resting, and let's say that we generated a graded potential. That graded potential can only travel a short distance, but I mentioned this last week. In order to create an action potential, we have to generate a graded potential first. In order to generate an action potential, if I want to really generate that full current that travels the whole length of the axon, it's got to start with a graded potential. So we have many graded potentials, many little mini impulses, but only if that graded potential is of a high enough intensity, only then will a graded potential become an action potential. Are you picking up what I'm putting down?
So does the stimulus is high enough to reach the threshold, does it start a new? Equates a new
Yes.
pulse altogether, or does it just get reinvigorated?
We're going to find that an action potential has pretty much the same steps of the graded potential. So we actually kind of do the same thing with a couple minor differences. Action potential. Okay, so if that graded potential was strong enough, we get to go ahead to create an action potential. Now, what do you notice about the action potential? The steps are almost the same. We depolarize the membrane, we repolarize the membrane, but the action potential has an added step called hyperpolarization. Let's talk about it, shall we? I'm going to skip ahead because I have a summary slide that I rather like. Ooh. Very exciting. Isn't this how you envisioned your beginning to the Thanksgiving holiday week? Talking about ions and soon to be neurotransmitters. I mean, it's a pretty good lecture today. We're going to be talking about excitatory postsynaptic potentials. Woo! Okay. So once we have a graded potential that reaches threshold, then we're going to initiate an action potential. It starts the same way, right? Here we are at rest. So we know at rest, the inside of the neuron is negative 70 millivolts. To depolarize the membrane, what do? Open sodium channels. Don't worry about activation gates and inactivation gates. We're going to keep it kind of simple. But if you look at the top, look at rest. This little area is closed, which means that sodium can't get in, it's closed. Once we depolarize the membrane, that's open, right? That's all we care about. So we depolarize the membrane. Sodium rushes in. And I want you to know this number. In an action potential, the inside charge goes all the way to positive 30. Woo! So we depolarize the membrane, we bring in so much sodium that the inside of the cell becomes positive 30. How many millivolt change is that? From negative 70 to positive 30. 100. That's not a great amount in the external world, but in a small microscopic cell, pretty good current. Okay, now I'm going to add in between here. We also spread that depolarization wave. Just like we did in the graded potential. Right, so it starts in one area, and when one area of the membrane depolarizes, it triggers the next area, the adjacent area, to depolarize. So if we were looking at right here, it would trigger this next area to depolarize. What I want to point out is, in an action potential, that depolarization wave only spreads one way. This is different from the graded potential. So in an action potential, that depolarization wave is only going to spread in one direction, like a true wave. That's pretty good. Whereas in the graded potential, the depolarization wave spread in both directions. Good. And then guess what? Just after we depolarize and the next area depolarizes, I repolarize. How do I repolarize? I close the sodium gates. At the same time as I close the sodium channels, I open up the potassium channels. So it's going to help the inside of the cell return to its resting charge. So it's the same basic setup. We flood the inside with sodium for a quick spark. And then we have a quick spark here, and a quick spark here. And eventually that spark leads to a current that travels the length of the axon. There's an added phase in an action potential called hyperpolarization. As the name suggests, we become even more polarized. So in hyperpolarization, we keep these potassium channels open even longer, which allows even more potassium to come out. So we let so much potassium come out that we get to negative 90. We hyperpolarize the membrane.
Like a normal oscillating principle to get back to the rest of the potential.
So let me show you this picture. So if you look at this graph, if we look at the purple, right? So this shows you the charge, the charge changes at resting negative 70 on the inside. We depolarize to positive 30. We repolarize, but then we go a little bit lower, and then we gradually come back up to resting. So it's not a gradual fluctuation all the time. It's only a gradual return to resting each time we go through this.
Is there a reason why
Of course. I'm going to tell you. Of course. Does that answer your question?
Yeah, well, the answer to the answer to my question is no. And it is today.
Okay. So why? I can give you two reasons why in an action potential, the membrane is hyperpolarized. Number one reason is to make sure that we get back to -70. So by overshooting it, it's in essence kind of a protection mechanism. By overshooting it and going even more negative, we are for sure guaranteeing that we get back to resting -70. Number two is this ensures that each action potential is separate. This in it goes even lower. This makes sure that each action potential is separate. In other words, it gives the membrane a little bit of a chance to get all of its shit together, to make sure that we have properly put the ions back where they need to go.
So it's like a recovery.
It's like a recovery period.
So it can't take on a new stimulus.
It's like you've actually read ahead. Maybe you have. You should just say yes. Yes, I don't go Christmas shopping. I eat, sleep, and breathe anatomy and physiology. In a minute, we're going to talk about that because the answer is yes. In some instances, we can start to generate another action potential even while we're finishing the first one. In some instances. Okay, but I'm trying to walk you through it here. Now, check it out. You can see this little note here. You know, we do send many action potentials per second. If I go back to our compare and contrast, way back there. The intensity of the action potential is always the same. So once we generate that current, it's the same intensity the whole length of the axon. So my question to you is, how do we make the overall intensity different? Like, if I have nerve endings and I touch something hot, isn't my body going to send a stronger nerve impulse signal to pull my hand away from that hot object? So how do we, if each individual action potential is the same intensity, how do we put together an overall stronger or weaker response? It's kind of like motor units, but we just send more impulses. Because look, you see this number at the bottom? You can send up to 1,000 action potentials per second. So this process of the sodium tunnels opening and closing, change in voltage, we can send 1,000 action potentials per second. So to generate a stronger nerve impulse response, you would send 1,000 impulses per second. A weaker response, you send 100 nerve impulses per second.
That's for action potential.
So if someone, let's say someone's like in severe pain and it gets to the point where they become, they can't really, because the neurons are overstimulated and overloaded, they pass out.
I don't know the answer to that question. I suppose that's one potential reason. I don't know why. I wonder if it's also has something to do with the region in the brain where the pain receptor responses are going. Yeah, so we can send more action potential. Each individual action potential is the same intensity, but if I want to make a stronger response overall, I just send 100 of them, or 1,000 of them per second.
Aren't you glad you're here?
Tell them Dr. J's there.
Yeah.
Yeah.
What am I gonna
Yes, title it is. Oh, stop it. Let's see.
Okay, so I just want to make a point here. We're not going to spend a lot of time on it. I just want to let you know, while this is going on this part of the neuron cell membrane, guess what? Over there, on that part of the neuron cell membrane, our friend sodium potassium pump is still working. So that's always turning, because it's always keeping more potassium on the inside, more sodium on the outside, which enables us to continue to manipulate these ions to get the benefit of the nerve impulse. Okay. That's okay. But some of it's gonna sink in. Well, I mean, more about, the folks that aren't here, they're gonna have to, and they're gonna hear this. So hi, folks that aren't there.
You guys.
They're gonna have to take time out of their weekend to do this, which is okay. Okay, so let's talk about some terms. We gotta talk about the term called propagation, and then we'll talk about saltatory conduction. Propagation is just the word that we use to say how that depolarization wave spreads. So when I said that we depolarize the membrane, we open sodium channels here. Sorry. And then we open sodium channels here. And then we open sodium channels here. So we have a spark, right? Propagation is just a fancy word for how that depolarization wave spreads down the axon. The depolarization wave propagates down the axon. It's a fancy word for describing how the depolarization wave spreads down an axon. Propagates. Like an example of a wave. Another example could be, the lights of a marquee sign where the light, each bulb comes on after each other. So this bulb comes on, and that one, that one. And it gives the illusion that the light is traveling around the sign. You know what I mean? That's another way to think about a nerve impulse. Each depolarization wave is a bulb coming on. So bulb comes on, bulb comes on, bulb comes on. It gives the illusion of the light traveling down. Okay. All right. So now I want to talk about saltatory conduction. If I can do this on my own. Like a big girl. Blank, blank. Hey. So we talk about propagation. Really, the propagation is referring to an unmyelinated axon. So when that nerve impulse, when that depolarization wave has to depolarize every single piece of the axon. We depolarize here, then we depolarize here, then we depolarize here. The depolarization wave spreads down an axon, that is unmyelinated. It has to depolarize every little bit. Versus saltatory conduction. Saltatory conduction, as you may have guessed, is how we propagate down a myelinated axon. So now we're going to have that myelin covering. You have that fatty myelin covering, remember? It's kind of fun to draw. If I could draw. So in saltatory conduction, we don't have to depolarize every little part of the axon. We only have to depolarize at the nodes of Ranvier. Remember that? So the nodes of Ranvier are the spaces. So in saltatory conduction, it's still the spread of the depolarization wave, but that depolarization wave is able to skip over the myelin. And because of that, this type of conduction of the depolarization wave is 30 times faster. If I don't have to depolarize every single area, if that depolarization wave can skip over the myelin, then I can get that action potential down the axon much quicker. "30 times faster." Here's a way better picture. So instead of having to depolarize every single area of the axon membrane, you only have to depolarize in the nodes of Ranvier. Isn't fat a good conductor of electricity? Yeah. So this is why we rely on having that myelin sheath in our peripheral axons. Almost all of our peripheral axons are myelinated, and that's how we can get our motor impulses out so quickly. You know, MS, multiple sclerosis, that is a condition, a disease that breaks down the myelin covering your peripheral axons. So a person with MS has trouble or the inability to contract some of the muscles. Not because their muscles aren't working, but because the nerve impulse is taking too long to get there. Because we're breaking down that myelin that usually speeds up the conduction. We won't go on the test, but just FYI, multiple sclerosis. Oh, no, not that. The fatty covering, the saltatory. Correct. This is showing saltatory conduction when that depolarization wave is able to depolarize, but then skip over a myelin sheath. Depolarize and skip over. So instead of having to depolarize every little bit, because there's myelin here, that depolarization wave can kind of skip a part of the axon. And it just means that the nerve impulse can travel faster. It just takes less time. You only have to depolarize here and then here. Then to do each section. The nodes of Ranvier is just the anatomical name for the space between the myelin. That's the naked part of that. It's the naked part of the axon. Good.
Thank you. Are there sodium channels on the dendrites too, or are those?
There are. There are. And a lot of times you're going to see more of the graded potentials here on the dendrites.
When it kind of jumps in between the nodes and bracket, how does it know it's still moving in one direction and not it's sticking apart? say that it can go either. That, no, right?
So it's easier to explain that if you're looking at an unmyelinated, because we know that after we depolarize one area and then it spreads, this area repolarizes. So because the preceding area repolarizes, it kind of prevents the sodium from going in that way. I believe it's a similar mechanism. There's of course more specifics to this that I don't know all the specifics of. But I believe it has something to do with the fact that this area over here repolarized. So if sodium channels are closed, I posted on Blackboard 2 video links. One of them is to a, I think it's to a crash course or whatever, but I know he talks more about this in that video link. So I encourage you to look at that.
What's the difference between a propagation and
They both basically mean the same thing, but when we use the word propagation, we tend to be referring to
just the movement?
how the depolarization wave occurs in an unmyelinated axon.
In this one, the oscillatory is still. It's just.
Correct. Yes.
Is the hyperpolarization then kind of a stopgap feature though?
I suppose that's part of it too, that if the preceding area is hyperpolarized, we're even farther. Because remember, to depolarize, you got to go to positive 30. So if I'm starting at negative 90, it makes it more difficult. Okay, here we go. So let's talk about some of the characteristics of these, bless you, of these action potentials. Action potentials, my friends, are very much like motor units. You thought you could forget about that. No, no, no. And a lot of these we've already discussed, excuse me. A certain threshold has to be reached in order to fire an action potential. I believe the threshold is negative 55 millivolts. I'm not going to ask you that, but typically the threshold to go from a graded to making an action potential is negative 55. Once we reach that threshold, the whole action potential fires or none at all. We already discussed that each action potential is the same intensity, but we can create a larger overall response by sending more nerve impulses in a given period of time. Good. We're about to add on more. We have these things called refractory periods, and this is what Olivia was talking about. Typically, the word refractory means kind of a rest period. Here, it takes on a little different meaning. Let's go to the picture. So here we see the electrical activity during an action potential. Inside of the membrane starts at negative 70, goes to positive 30, back to negative 70, hyperpolarizes, gradually returns to negative 70. Look at this darker blue area. This is called the absolute refractory period. Basically, it's during depolarization and the beginning of repolarization. So it's during depolarization and beginning of repolarization. When a nerve is in the absolute refractory period, it means that even if we send another stimulus, it is not possible to start another action potential. During the absolute refractory period, while a nerve is in the middle of depolarizing and the beginning of repolarization, even if we send another stimulus, it cannot generate another action potential. That's what it says on the previous slide. Membrane is not responsive to additional stimulus. I mean, the axon is still busy doing the first action potential. And then we have a relative refractory period, which is this lighter blue. And that is during the end of repolarization and during hyperpolarization. During the relative refractory period, it is possible to make another action potential, but you need a stronger stimulus. In the relative refractory period, it is possible to begin another action potential only if that stimulus is stronger. So we would only need to do that if we wanted to send a really strong nerve response, if I'm touching something hot or something, you know? I mean, of course it happens more than that, but I'm just saying. Threshold for producing action potentials is increased. So we can only start another one if the stimulus is stronger. So you should know the definitions of these two. You should know when it occurs and what's possible, right? So I said during the absolute refractory period, that is during depolarization and the beginning of repolarization. And it is not possible to start another action potential. During the relative refractory period, during the end of repolarization and hyperpolarization, it is possible to start another action potential. You just need a stronger stimulus.
So if you actually want to stimulants, we need nerves to still us to move your arm, right? So if you have a constant stimulus, is it just going to keep going like up, basically?
No, because, well, think about that. You mean like once it gets into the muscle?
I'm not really worried, but like if you have, like it's not, so if the refractive, the absolute refractive period is it's short, the polarization is so short. But if you have a constant stimulus, it's not gonna stay in that period.
No.
It has to recover. So that
Correct.
if you're constantly sending another stimulus, the graph is just kind of
A little bit. And what we're going to find out is, it might be in the next slide, just like we could have summation with the motor units, where if we sent more and more nerve impulses to the muscle would more easily get to contraction. If we send so many action potential stimuli, it's going to be easier to start another one. And they do kind of summate and back up on each other a little bit. It's gonna be kind of nice to not have lab tonight. I mean, I love this class, but it is late, you know? Getting home at 8 is much different than 10. Okay. Sure. All right, now, we are not done. So I know this is kind of a weird picture, but I like it, so I think that they had their Wheaties when they made it. So we just finished talking about that action potential, right? And we know that that action potential can only start if our gradient potential reached threshold. So it's almost like we started at rest And then we generated a graded potential that was at a high enough intensity to trigger an action potential. And then once we send the action potential, it's going to go the full length of the axon, no matter how long it is, right? Well, what happens when we get to the synapse? There's a space. How are we going to get that electrical current across the space? Which is an example of a neurotransmitter. Be still, my beating heart. Right? See this long jump dude? You get it? That's why I make the little bucks, folks. I just want to remind you that we have these synapses in multiple places, but you don't have to know these specific names. We're going to be talking about these chemical neurotransmitters, which are more common. It is, in very rare instances, it does happen that the end of a nerve actually touches something directly, but that's much rarer. We're going to be focusing on the more common neurotransmitter synapse situation.
Sorry, what did you say we didn't need to know?
You don't need to know these. Sure. How much for the peanut gallery? Sometimes it depends on how much time we have. Every class is a different pace. No, it's okay. At least I tell you what you don't have to know. And I stick to it, right?
Yep.
Because I know this class would tell me if I did. You're on top of it. We're going to focus on these chemical synapses. All right. This is the beginning of what you already know. See, aren't you glad that you paid attention and studied so well when I had the muscle chapter? Because this is reviewing exactly what we discussed in the neuromuscular junction, right? You may recall a nerve impulse comes to the end of the axon. In other words, the action potential, which is the end of the axon. That triggers calcium to come in. When calcium comes in, it triggers these vesicles to be released, or to move to the end of the axon, and it releases the neurotransmitters that cross the synapse. That should be a review, right? So the action potential, which is the end of the axon, calcium channel is open, the presence of calcium triggers these vesicles to move to the edge, neurotransmitter is released. It's neurotransmitter that crosses the synapse. But now we're going to pick up where we left off because we haven't talked about what happens in the postsynaptic membrane until now. Dun, dun, dun. So now, okay. So now we're going to follow what happens after that neurotransmitter crosses the synapse. That neurotransmitter crosses the synapse and it binds to a receptor. And that's what they're showing you here. That neurotransmitter crosses the synapse and it's going to bind to a receptor. We call this the postsynaptic membrane. It could be a muscle, it could be another nerve, it could be anything. I'm going to skip ahead because I want to use two examples to demonstrate what could happen. So let's go back to our example that we already talked about, acetylcholine. Because we remember, acetylcholine is acetylcholine is a neurotransmitter that crosses from a nerve into a muscle, right? Always, always, always. What's going into a skeletal muscle is acetylcholine, ACH. acetylcholine is an example of a neurotransmitter that when it crosses the synapse will bind to a sodium channel. So you should know this example. Acetylcholine, we know that it crosses the synapse into skeletal muscle. And it just so happens that acetylcholine crosses the synapse and binds to sodium. Well, guess what? When that acetylcholine binds to sodium, sodium channel opens. Guess what happens? Sodium rushes into the cell. If all of a sudden sodium rushes into a cell, the inside of that cell becomes positive. In essence, we've created a depolarization. And that's why the effect of acetylcholine at the muscle is excitatory. Because acetylcholine binds to sodium. Sodium rushes in, and we create a spark, just like we did in all the other examples. That spark excites the muscle. It tells the muscle to do what it does. In my other section, I gave the example of a stoplight. And that's kind of how neurotransmitters work, which is to say that if it is binding to a sodium channel and the effect is excitatory on the postsynaptic membrane, it's like giving a green light to your postsynaptic membrane. So it's telling green light, in this case, muscle, green light, do what you do, contract. Because it's not like the neurotransmitter, you know, sometimes we say a neurotransmitter is a chemical messenger or whatever, same thing with the hormone. It's not like the neurotransmitter leaves a detailed message. It says, hey muscle, I want you to contract at 8 kilograms of tension for 1.2 seconds. No. These neurotransmitters, when they bind, either excite or inhibit. So it's like a green light or red light. And when a neurotransmitter binds to a sodium channel, it causes depolarization, creates a spark that excites. On the other hand, let me give you an example of an inhibitory neurotransmitter. An example of an inhibitory neurotransmitter is dopamine on certain receptors in the brain. So here, it's the same beginning steps, but instead of acetylcholine crossing the synapse, it is dopamine. And now dopamine is going to bind to a potassium channel. When dopamine binds to that potassium channel, it allows potassium. We have more potassium on the inside of the cell, right? The potassium is going to flow from high to low. So potassium will flow from the inside of the cell out. And when that postsynaptic membrane loses a bunch of positive ions, it actually turns the inside of that membrane more negative because we just lost a whole bunch of positive ions. So when a neurotransmitter binds to a potassium channel, potassium flows out, hyperpolarizing the membrane. If you hyperpolarize the membrane, you're making it harder to make a spark or to depolarize. So the effect is inhibitory. It's like giving the red light to the postsynaptic membrane. So when it binds to these channels, the ions will flow from high to low. So we just have to go back to remembering that there's more potassium on the inside. So if I open this channel, there's always going to be more potassium on the inside. It's always, in these, it's diffusion, it's passive. It is facilitated diffusion by a channel, but there's no ATP. But just by opening this channel, we gotta look to see there's more potassium on the inside. So it will go from the inside out. Because sodium, we always have more sodium on the inside. I mean, on the outside, excuse me. So when I bind to a sodium channel, the concentration gradient is going from outside to inside. If I was a better computer person, I could get rid of this message, but I don't know how to do it. So. If it binds to sodium, if it binds to potassium, it will hyperpolarize the membrane. Okay, good. Good. So that's basically saying what all these other things said. If you know those two examples, right? So you should know those two examples. I gave you an example of acetylcholine crossing into a muscle, and acetylcholine binds to a sodium channel. Sodium comes in, depolarizes the membrane, the effect is excitatory. Then I gave you an example of dopamine. When dopamine is released across the synapse to other neurons, it binds to potassium channels. Potassium flows out, hyperpolarizes the membrane, the effect is inhibitory. Now, we actually give fancy names. If stop at 7:20, right? All right, I want to finish this chapter, but we should be able to, literally. We give these names. If the effect is excitatory, we've generated an excitatory postsynaptic potential. My example of acetylcholine going into muscles, we've generated another little impulse. Sorry. I'm on slide 68. So the example I gave of acetylcholine into a muscle is an example of an excitatory postsynaptic potential, because the membrane post-synapse, the membrane after the synapse is excitatory, it's excited. The example I gave of dopamine is an example of an inhibitory postsynaptic potential, where the postsynaptic membrane is inhibited. Just a fancy name for what we're talking about. Okay, rapid fire. Most of the rest you don't need to know. A couple of things I'll point out. Your organs and tissues are going to receive both. So it's not as if it's only going to be one neurotransmitter floating around. So just imagine that we have many different neurotransmitters. And sometimes you're going to get some messages that are excitatory to an organ and some messages that are inhibitory. It happens. The resulting action depends on, is the result of, whatever there's more of. If a muscle receives 100 excitatory messages, and 10 inhibitory messages, what is the resulting action going to be? It's still going to excite. So I'm just pointing out that we have a lot of neurotransmitters floating around. And you might get some excitatory and some inhibitory. Whatever there's more of, that's going to be the net response. These postsynaptic potentials can summate. You don't need to know the difference between temporal and spatial. I'm just saying that if we send many acetylcholines to a muscle, the effects can summate a little bit, they can add on to each other. All right. The very last part of this chapter just goes into detail about some of the other examples of neurotransmitters. We have a whole bunch of them. Just make a note here. Some neurotransmitters are only excitatory, some are only inhibitory, but some can be both. Right? So some neurotransmitters are excitatory when it binds to this tissue, but inhibitory when it binds to that one. Dopamine is an example of that. The example I gave you was an action of dopamine where it's inhibitory. But if that dopamine binds somewhere else, it can actually be excitatory. Some neurotransmitters act indirectly where they have to bind somewhere else to trigger something else to happen. And of course, neurotransmitters can only bind to a specific receptor. So acetylcholine can only bind to an acetylcholine receptor that's related to sodium. Dopamine can only bind to a dopamine receptor that happens to be related to potassium. But they're specific. So we just have these neurotransmitters floating around, and whenever they bump up against the matching receptor, they'll bind. But they can't bind to everything. Perfect timing to finish this chapter. So I've given you a list. The only two examples I want you to know are the ones I've already given you, right? You only have to know acetylcholine at muscle and dopamine when it synapses with other nerves. These are all extra. So if you've heard of SSRIs, selective serotonin reuptake inhibitors, you know, a lot of medications have their influence on neurotransmitters. If you know what a neurotransmitter does, you can manipulate that. If it excites something, I can give a medication that's going to make more receptors available. So I can get more excitation. Or in the case of the SSRIs, selective serotonin reuptake inhibitors. So I inhibit the reuptake of serotonin. If I inhibit the uptake of serotonin, there's more serotonin left floating around, which can make someone feel happier. You don't have to know all of the neurotransmitter classifications. That should make you feel good, right? But I am going to point out one thing. Because you're going to hear this again if you haven't already. Have you heard of cholinergic and adrenergic? So a lot of times medications are classified as such. So all I would like you to do, pair together anything that says cholinergic, it's talking about fibers, neurons, that release acetylcholine. So group those together. Cholinergic means it releases acetylcholine. And I know it's 7:20, I'm going to be done in like a minute. And the way that I remember that is cholinergic begins with a C and it has a C in the name. Versus adrenergic is just referring to a fiber that releases norepinephrine. We're gonna come back to this in our final chapter this semester on the autonomic nervous system, but for right now, just pair those together. Cholinergic, acetylcholine. Cholinergic releases acetylcholine. Adrenergic releases norepinephrine. That's it. Now, you can even have further subdivisions. So the cholinergic receptors can be nicotinic or muscarinic. You don't need to know those. The adrenergic receptors can be either alpha or beta. Whew. Don't worry about that. You're waiting across the So I've given you some examples. These are just for you. I try and give some clinical examples. And I give you some examples of medication. So feel free to read through these, but it won't be on the test. When you see the name anticholinergic, if it's against the cholinergic, it's blocking acetylcholine. Because cholinergic means acetylcholine, right? I'll give you an example of albuterol, right? It affects the adrenergic receptors, right? Which means norepinephrine. Not going to be on the test, it's just extra. I am all done. Have a good holiday. You want to stop?